Hello folks, our next section on vectors deals with some things called parametric equations. So here's the main idea going forward. The relative position of a moving object is dependent upon its starting position and its velocity at any given moment in time. So go ahead and write that. Basically, this is an extension off of applications of vectors. So we learn about vectors in 2D and 3D. They're very basic properties, and then we talk about where they're actually used. Parametric equations is one of the more helpful ways that they are used other than describing forces. Talking about objects' movement in terms of time. And you're going to notice that we're going to incorporate like equations of lines into this idea. Okay, so let's also draw a scenario of what we're talking about. So basically, and we're just going to do this in two-dimensional space. We're not going to worry about three-dimensional movement. But in two-dimensional space, let's suppose I have a line that'll go through the points P1, P2. So if this is point P1, its coordinates are x1, y1. And let's say it goes over here through point P2, which is x2, y2. And let's suppose that that line is parallel to a vector A, which the components of vector A would be A1, A2. If we were to create a vector from the line P1, P2, so again, specifically, what if I wanted a vector P1, P2? So just a portion of that line, right? Because lines go on forever. Vectors have magnitude. They have length. So if we take a portion of that line, then it would have to be a scalar multiple of vector A. In other words, in this case, our scalar multiple is going to be t and then times vector A. Because if they're parallel to each other, they're going to end up having the same slope. Okay, now t in this case is our scalar, right? It is also called the parameter. Parameter. Usually it stands for time, which is why they chose the variable t. Usually stands for time. Okay, so notice both sides of this equation are a vector, right? Vector P1, P2, vector A. So I could kind of expand each of these and write an equation. So we find vector P1, P2 by subtracting the points from P1, P2, right? So like if I look at the points, I'm going to do, we always do the second point first. So I get that from doing x2 minus x1. That's how I'm going to get the vector. And then the y coordinate comes from y2 minus y1. So that's how we get vector P1, P2. And then this is going to equal t times vector A, which vector A is denoted by A1, A2. Okay, this is the first takeaway from today. This is called a vector equation of a line with parameter t. Vector equation of line with parameter t. So notice we have more than just a few variables. Typically a line, is y equals mx plus b, where you have a point and you have a slope and all that kind of good stuff. This one, we have 2 points, which is typical, right? If you think about like point slope form of a line, 2 points, which is typical. Instead of slope, the slope is kind of denoted by the given vector. And then t, obviously, as we keep mentioning, is time. So I'm going to write a question here. Again, you can abbreviate these questions if you want, but it's important that you actually at least write them. That way you know when you're looking at your assignment or studying for your test, you kind of know what the question types are going to sound like. Write a vector equation describing a line passing through point P, which will be at 1, 4, and parallel to vector A, which will be at 3, negative 2, and determine the object's position at t equals 4. So basically, we said that these types of equations are helpful for movement, okay? So I want you to write the vector equation describing the line that goes through a point. It's parallel to this. So again, this is very, very similar to point slope form of a line, which if you remember point slope, I'm just going to write out here to the side to jog your memory, is y2 minus y1 equals m times x2 minus x1. Well, this is very similar, except we have a parameter t, and we have, instead of slope being m, our slope is just going to be parallel to a vector. Okay, so here's how that works. If I have, if I use this given points that they tell us as x1, y1, and then instead of vector, I got to make sure I put my vector notation above a. Instead of a slope, vector A has components a1, a2. If I plug these 4 numbers in, now this part here is the second part of a question. Determine the object's position at time equals 4. I don't want you to plug in t equals 4 until after you've established the equation. Okay, so if I plug this in the vector equation from here up top, that's going to be the vector x2 minus x1. Well, I don't know what x2 is, so I'm going to leave that there. Minus x1 is 1, comma, y2 minus y1 is 4. Is going to equal, again, we're leaving t as the variable, and then a vector a1, a2. So that's going to be 3, negative 2. Okay, now typically you won't see the x2s and the y2s here. The x2 and y2 just stand for any other coordinate points. So typically you'd see it written like this: x minus 1, y minus 4 is equal to t times the vector 3, negative 2. So this is step 1. That is the equation, the vector equation of a line that goes to the point 1, 4, and it's parallel to this vector. Part 2 is, what is the object's position when time is equal to 4? So at that point, what that's going to allow us to do is, when you plug in a variable for time, it's going to allow us to solve for the object's position using the x and y coordinates. Okay, so here's what that looks like. When time equals 4, that means that our vector is going to be x minus 1, y minus 4 is equal to, we're substituting in 4 for time, 3, negative 2. And then look what happens. So if we leave the left side alone here, if we simplify the right side, if we distribute in this scalar of 4, then we get the vector 12, negative 8. And then, by definition, anytime we have a vector equal to a vector, then its components are equal as well. Right? So this x component, x minus 1, is equal to 12. So let's write that. We have x minus 1 is then equal to 12, and the y components are also equal. Y minus 4 is equal to negative 8. And now these only have one variable, so then I can solve. If I add 1 to both sides, I get x equals 13. And then if I add 4 to both sides in this one, I get y equals negative 4. So that means when time is equal to 4, then the object's position, time is equal to 4, we'll say that implies position is going to be at the coordinates 13, negative 4. Okay, so you use your parametric equation, your vector equation to find that object's position at any given time. Okay, now I keep saying parametric equation because that's what we're going to talk about next. I want you to, so this will be our second question. I want you to write, make the font bigger. Okay, write the parametric equation from the vector equation in part 1. So our vector equation that we just found is this up here, x minus 1, y minus 4 equals t times vector 3, negative 2. So here's what a parametric equation is. Or actually, I should say write the parametric equations because there are two. So basically, it keeps t, since t is your dependent variable, okay? T is your dependent variable. It wants us to write two separate equations that solve just for x and y, kind of like we did up here. So if the equation that we were using was x minus 1, y minus 4 equals t times 3, negative 2. So this was the vector equation. Notice it's in vector form, right? We have vectors in it. In order to write the parametric equation, we are going to first distribute in the scalar of t. So that'll be x minus 1, y minus 4 equals, distributing in t will be vector 3t, negative 2t. And then again, we have a vector equal to a vector. So then just like we did up here to solve for a particular position at a particular time, we're going to set the x values equal to each other. So x minus 1 equals 3t. And then we're going to set the y values to each other. Y minus 4 is equal to negative 2t. And then if we add 1 to both sides on this one, then we get the equation x equals 3t plus 1. And then if we add 4 to this equation, we get y equals negative 2t plus 4. These now look very, very similar to slope-intercept form, y equals mx plus b, except our parameter t, standing for time, that's the dependent variable, and that dependent variable tells us where the x and the y are going to go. So please note, the vector equation is the exact same thing as the parametric equations, right? These two things are completely equal, it's just a different notation. Okay, so in general, let's talk about parametric notations in general. Parametric, we'll say equations rather, in general. If we take our vector equation that we circled up here in blue, and I do the same thing, right? I set the vectors equal to each other, and then I split them apart into an x and a y. In general, I'm going to get that the x coordinate is found by doing x1 plus t times the part of vector a1, and that the coordinate y is done by y2, plus t times the part of the vector a2. Now, this is nothing you have to memorize. If you can remember the equation for just the vector equation, then you can remember this. And I think you're going to find as we do some examples, it's actually going to be pretty easy. So let's do some examples of each. Number 3, I want you to write a parametric equation of y equals, I'm actually going to give you the equation of a line now, but I want it in a parametric form. Y equals negative 4x plus 7. And basically I want you to remember that in a parametric equation, t is an independent variable, and x and y are both dependent. So let's add that up here. In a parametric equation, t is the independent variable, and x and y are both dependent now. So that's different from what we're typically used to. So here I have a regular old line, but if I want a parametric equation, that means I'm going to be talking about an object moving along that line, and if I want to find its given position at any point in time. So basically, if we know this, if you can remember this, that the t is the independent variable, and x and y are dependent variables. If we think back to in the equation of a line that x is independent, right? So in a regular line, x is independent and y is dependent. Then we're claiming that in this case, x is almost going to act as t because t is the independent variable. So let's do that. Let's suppose I say, what if x is equal to t? So these represent both of my independent variables in their separate equations. So if t is my independent variable, if I substitute that in to the given equation, so instead of x I plug in t, then I get y equals -4 instead of my independent variable, what used to be x, in a parametric equation, independent variable is t, I get +7. These are your answers. And I should have written, the parametric equations, because there are going to be two equations, one for x and one for y. So these two parametric equations describe the same line as y equals -4x + 7, right? So these literally mean the same thing, except this adds in the added element of time to talk about movement. So it's that simple. Let's do another one. Same directions. Writes parametric equations. This time I'm going to write, you're going to need two, for, or of the line, y equals, or no, let's do a different, let's do standard form of the line. 3x minus 4y is equal to 12. So if I want to write this in as a parametric equation, and it's not already in slope-intercept form of a line, we need to go ahead and move some things around first to make that happen. So if I want to get this in slope-intercept form first, I'm probably going to go ahead and subtract 3x from both sides. So then we get -4y equals 12 minus 3x. Well, let's write it the other way, right? Slope-intercept form is typically a slope first, -3x plus 12. And then if I go ahead and divide everything, in order to isolate y, divide everything by -4, both terms on the right-hand side are going to be divided by -4. This going to be y equals -3 divided by -4 as a positive 3/4 x. And then 12 divided by -4 is going to be -3. So this is now in slope-intercept form. And now I'm going to use that to write my parametric equations. Well, the first parametric equation is the same every single time. X equals t will always be one of, I'll say always be first, because typically you do that one first, parametric equation. And then to get the second parametric equation, you simply are going to substitute t in for x instead in your original equation. So in this equation, y equals, instead of 3/4 x, we're going to have 3/4 t minus 3. So these are your two parametric equations of the line 3x minus 4y equals 12. That's simple. The only hard part sometimes is if I give you a line in standard form like I did here, instead of slope-intercept form, you just have to rearrange it first. Okay, number 5. I want you to write an equation in slope-intercept form. Not slow-intercept, slope-intercept form of a line that has parametric equations of x equals -3 plus 4t and y equals 3 plus 4t. So now this is going to go backwards. The last two problems, I gave you slope-intercept form. You had to tell me parametric equations. And then now we're going backwards. Now, in terms of writing your own parametric equations, x equals t is always going to be your first. However, if you do some algebra, sometimes it doesn't necessarily mean that every parametric equation is going to have one that's x equals t. Like in this case, I don't have that direct relationship between x and t. They're giving me these two similar looking but different equations for x and y. So when you go backwards, what you need to do, first step, step 1 is to solve both equations for t. So let's do that. Solve both equations for t. So in that first equation, x equals -3 plus 4t. I'm going to go ahead and add 3 to both sides. So then I get x plus 3 equals 4t. And then to solve it for t, I'm going to divide everything by 4. So then I get t equals x plus 3 over 4. Now technically, could you write this as 1/4 x plus 3/4? Yes, absolutely. But I'm going to recommend that you leave it in this form because the next part's easier if you do it that way. Now, you could write it out the other way and still solve the problem just fine, but personally I think it's easier to keep it this way. Let's solve the other one. Y equals 3 plus 4t. So again, let's subtract 3 from both sides. We get y minus 3 equals 4t. Divide everything by 4. And then we get our second equation of t equals y minus 3 all over 4. So step 1 is to solve each equation for t. Step 2, as you might imagine, now if they both equal to t, then we're going to set those equations equal. Set those equations equal, because then that's going to eliminate the variable t altogether, giving us our regular x and y relationship for a line. So then I have x plus 3 over 4 equals y minus 3 over 4. So it kind of, instead of writing those as we would have before, like 1/4 x plus 3/4 equals 1/4 y minus 3/4, if you do it this way, then notice I can get rid of the fractions extremely quickly if I multiply everything by 4, which you could do in the other way as well. So if I multiply everything by 4, my denominators on both sides cancel, leaving me with x plus 3 equals y minus 3. And then if I'm writing the equation in slope-intercept form, I need to isolate y. So I'm going to add 3 to both sides, giving me the final equation of y equals x plus 6. Y equals x plus 6. Let's do one more. Same directions as before. Right in slope-intercept form. Given, and I'm going to give you 2 parametric equations again. Okay, given our 2 equations, x equals -4t plus 3, and y equals 5t minus 3. So I want you to write one equation in slope-intercept form. So as we did earlier, we are going to solve each of these equations in terms of t. So if I have x equals -4t plus 3, if I subtract 3 from both sides, I get x minus 3 equals -4t. Divide everything by -4, and then I get t equals x minus 3 over -4. Again, if you want, you could divide this out right here and right now. I'm going to leave it as is. Y equals 5t minus 3. Add 3 to both sides. We get y plus 3 equals 5t. So then to isolate t, we need to divide everything by 5. So we get t equals y plus 3 all over 5. So step 1 is solving each of the equations for t, and then step 2 is setting those values for t equal to each other. So then we have x minus 3 over -4 is equal to y plus 3 over 5. And then your job is to write this in slope-intercept form, so to solve for y. Now, the last time, both of the denominators were the same. So we multiplied everything by 4, and we got rid of our fractions, and everything was good. In this case, our denominators are not the same, so I recommend that we cross-multiply. Now, in doing so, the only thing you have to be cautious of is when you cross multiply x minus 3 times 5, that 5 needs to distribute to both the x and the negative 3. So that's why I'm leaving it in parentheses here. Same thing with the negative 4. It needs to distribute to both the y and the positive 3. So then if I distribute those, I get 5x minus 15 equals negative 4y minus 12. And remember, I'm trying to solve for a y, so I'm going to go ahead and add 12 to both sides. I'm going to combine that with negative 15, so negative 15 plus 12 is negative 3 equals negative 4y. And then to isolate y, divide everything by negative 4. So then I'm going to get y equals negative 5/4 x, and then negative 3 divided by negative 4 will be plus 3/4. So this one's a little bit more difficult, not difficult, just a little bit more challenging because of those fractions that have the end. So either you get your fractions at the beginning if you want, up here when you solve for t and deal with them early on, or me, I kind of like to deal with them, get rid of them by cross multiplying and then deal with them at the very end. So that is your lecture on vector equations, which will look like this. Vector is equal to t times another vector, and the parametric equations, which look like this, but that's a little bit more complicated. I want you to think about slope-intercept form of a line being solved for your first parametric equation, which will always be x equals t, and then just solving for the y.